My name is Kamau. I work as a functional developer for Hyman Technologies, which is a software engineering consultancy based in Berlin that also offers fully remote employment. Really cool company. Highly recommend it for anyone looking to change. And my talk today is about streams. So just a second. Okay. And well, streaming is all about streams. So this flow of potentially infinite elements that become available over time. So this unbounded sequence of data. So many aspects of our application embody some form of data flow oriented programming. Streams can be results, result sets coming from a database. They can be requests coming into your web service. It can be responses to those requests. Event source applications can be built using streams. You could even list files in your file system and get back a stream. You may even decide to build your application in a streaming-oriented data flow manner, even though you're not necessarily streaming data. And there are multiple advantages to doing this. So why would you do that? Well, streams bring a declarative style of programming to your application, a pipeline, if you may, that expresses what's being done without necessarily saying how it's being done. You know, this leads to a code base that's more fixed on the results rather than the mechanics behind those results. Streams are inherently concurrent. So ZStreams have multiple operators that allow us to do things concurrently, minimizing latency. Streams are inherently resourceful. They hide the opening and closing of resources and do it for you. You don't have to worry about the acquisition and release of resources, well, because that's baked into streams. These guarantees hold in the presence of concurrency, interruptions, even errors. So you really never have to worry about leaking resources. The ZStream type has 3 type parameters that have similar meaning to those described by the ZIO type, right? So you have the environment type, so the required environment. You have the error type by which the process may fail, and the type by which the process may succeed. The only difference is while a ZIO produces exactly one value of type A, ZStreams produce 0 or more, or probably potentially infinite values of type A. ZIO streams are pool-based streams as opposed to push-based streams such as Akka streams, right? So nothing happens in a ZStream until you run it. So until you pull values from it. You can view running a ZStream as converting that stream into a ZIO effect that is then run to produce a value. So that's a multi-step sequence. ZStreams are automatically chunked. So when you're dealing with ZStreams of int or strings, you're actually dealing with ZStreams of chunk of int and string respectively. You never actually have to deal with the raw values. And this is done obviously for better performance. Constructors. Well, ZStreams provide multiple constructors that we can use to create streams. You have your typical apply function method, which is used to create literal streams. You have the from iterable, which converts any Scala collection type into a stream. You can also make streams from a ZIO data type, such as queues. Now, something quite interesting about queues here is that if you have a push-based stream, such as Akka stream, you could wrap it in a ZStream by a queue that gives you a place to push the values, and then convert that queue to a stream, ending up with a pool-based stream. That's really cool. You can also make streams from ZIO effects. Operators. Well, ZStreams come with a huge assortment of operators, including take, which, well, pulls the first n elements from that stream. Take while pulls elements from a stream as long as the specified condition is evaluated to true. Now, there's an interesting point to note about take and take while. They do as little computation as necessary to satisfy their respective conditions and no more. So they're quite effectful in that sense. Then you have drop that drops the specified elements from the stream. You have drop while that just drops elements from the stream as long as a specified predicate condition evaluates to true. Then you have map. Now, the function you provide to map is applied lazily. Remember that. So if you were to pull, say, 2 elements from the stream before calling map, then only those 2 elements would be mapped. Then you have filter that filters elements emitted by this stream using this provided function. Then you have forever. Forever is how you concatenate a stream with itself an infinite number of times. Okay, it replicates the stream and all of its effects. So in an example here, we have if the stream was a database query, okay, that's producing one value, then that value and all of its effects will be queried 5 times. So remember, you are taking the stream and concatenating it to itself 5 times and all of its effects. Then you have run head, runs the stream to completion and yields the first value emitted, discarding the rest of the elements. So yeah, something to know here is that run head actually runs the stream to completion. Okay. Then you have the concat or concatenate, the plus operator. Now, this function, this plus operator is lazy. So in an example here, elements of the first stream are streamed before elements of the second stream. Remember we said streams are resourceful? Well, if 2 streams were database queries, okay, the 2 stream 1 and stream 2 here, stream 1's query will be run, its result set streamed out, its connection released back to the connection pool, and then and only then would a new connection be acquired to be used in the second stream, and so on. So the first stream is streamed out completely and its resources released before the second stream is even streamed. Resources are freed as early as it is safe to do so. There are obviously multiple other operators we can use on streams. If you have used the Scala collections before, then many of those methods apply. Now, there are certain major differences on how streams and streams operate as compared to collections. Remember, streams are mere descriptions of how to produce values. So here we have this input variable that's used to, which itself is a stream. It's used to create 2 other streams, and those 2 other streams are concatenated. Now, if variable, the input there represented, say, results from a database query, 2 queries would be carried out. One for evaluating stream 1 and another one for evaluating stream 2. So you can imagine if the state of the database was to change in between running the first query for stream 1 and running the second query for stream 2, I don't know, maybe some records were deleted or new records were added, the end results would probably not be what you expected. Operations performed on a stream map are applied up to the very first point where that stream was being created. Okay. There's another interesting pitfall that you may face when using the concat function. If you concat 2 streams, then the first stream is streamed entirely before the second stream is streamed. So if you concatenated two streams, then called runhead, on the first stream, stream 2 would not even be evaluated, right? So, and the reason is when concatenating two streams with a plus plus operator, the second stream is evaluated only when all these elements of the first stream are exhausted. So in this case, we're only taking the head of the first stream, so we'll never get to the second stream. What you probably want to do, so you probably want to watch out for that. The other pitfalls we can talk about, say if you concatenate an empty stream with a non-empty stream, then you obviously get the non-empty stream. No surprises there. But if you right zip an empty stream with a non-empty stream, you get back an empty stream. Right? The zip function, so right zip, left zip, and zip are all implemented in terms of flat map. So what you're actually doing here is flat mapping an empty stream, which obviously results to an empty stream. This is something that you definitely want to be careful about. So if imagine you have this big chain of complex pipelining involving multiple streams that are concatenated via flat map. So any of the zip functions. An empty stream somewhere in the middle short circuits the rest of the pipeline, resulting in an empty stream. Okay, this can be quite hideous to debug, and so you probably want to be careful when using flat maps on streams. What you probably want to do is concatenate the streams. You might want to run the first stream only for its effects, in which case you could call drain on the first stream, then concatenate the other stream. The drain function converts the stream to one that executes its effects and emitting no elements, pretty much. All right. Just as you have ZIO fail, we also have ZStreams fail, right? So that's the same. You can also recuperate from errors using catch all or else, and many other functions that you're familiar with if you have used ZIO, including the various variations of retry. Now, one important note about stream is that if there's some failure in the stream and you retry that stream, it will be retried from the very beginning. There is no way of retrying only the last failed portion. You only get, and then the other thing is you only get one error type, regardless of where that error occurred in the stream. So if you're making, say, a stream connector, right? You should handle the retry in the actual connector. So if the connection fails, since you still have the offset at hand, you could try reestablishing a connection, then using that offset, try reading the next chunk. Right? If you don't do it there, in case of connection errors, the users of your connection will have to restart the stream from the very beginning. Obviously, that makes sense for conditions in which you can recuperate by merely trying. Maybe because you have flaky connections, and usually trying one or two times solves the problem. Sinks. So while streams produce values, sinks consume them. So both streams and sinks are aspects of the same type, the channel type, right? This low-level type that can read on one end and produce values on the other. The sink type parameters include the required environment type, the error type by which this stream may fail. Remember, a stream can only fail with one type, okay? Then you have the input type of the stream. So the type of the elements the stream consumes. You have the leftover types, and then the type by which the sink succeeds. Okay, so a sink can run forever, so consume input forever. It can fail with a specified error type. It can consume all elements of the stream and succeed with a specified success type, or it can consume some elements of the stream and have some leftover types of the specified leftover type. Now, as you can see, we have two type parameters that essentially define the same elements, right? We have the input type that represents the value that the stream consumes, right? And then you have this leftover type that represents the values from the stream that we don't consume. Logically, these elements are the same type, right? And the reason why the developers of ZStream decided to, Sinks in this case, decided to use the two types is variance, right? So the input type is contravariant because that's what the sink reads, while the leftover types is covariant because that's what the sink also produces. If we had only one type, right, that's the input type, right, which then discard the leftover type. So that would mean defining the input type as invariant. Every single sink would need to take a type parameter, so the input type of that sink. Well, why? Because Scala cannot infer invariant type parameters. Adding that extra type would bring so much noise to the API. So the alternative of having both the input type and the leftover type seems like the better compromise. So sinks are used for running streams, right? Consuming elements of the stream. Sinks can be chained to consume elements in a flat map-like manner. You can imagine consuming a stream containing HTTP status. Here we define methods to retrieve the HTTP method, path, and version. We chain the three sinks in a for comprehension and get a single sink that succeeds with a tuple. The single sink will consume values and feed them to HTTP method until it's done. And then it will accept more values and feed them to HTTP path until it's done. And then it will accept more values and feed them to HTTP version until it's done. A really cool feature here is that the next sink in the composition will be fed leftovers from the previous sink before additional elements are retrieved from the stream and fed to that sink, right? So any leftover elements from HTTP method will be first fed to HTTP path before new additional elements are pulled from the stream and consequently fed to the same sink. All right, so just like ZStream, ZSinks have many useful constructors and operators, including count, take, for each, and zip. Well, there's actually a potential pitfall to watch out for when using zip and zipar operators with sinks. If you used zipar on two sinks, well, every element of the source, of the input source, would be fed to both sinks at the same time, simultaneously. So say we defined a sink that both counts elements and sums them up, returning a tuple containing both results. Now, sink 2 here would return a tuple containing the values 4 and 0, while sink 1 would actually return the values we would expect, 4 and 10. Zip does things sequentially. So it will wait until the first sink is done before moving to the second one. Now, since this first sink is consuming the entire stream, well, then no values are actually passed over to the second stream. So the second stream, you don't even get to the second sink, sorry. So zipar, on the other hand, does what we'd expect because all the values from the stream gets fed to both sinks simultaneously at the same time. So that's the reason why zipar here returns the values you expect. So that's probably something you want to watch out for. Pipelines. Well, pipelines allow us to transform elements of a stream in a compositional standardized manner. pipelines are too many transformations. The data types include the environment type, so the error type, then the type of input elements that this pipeline will be transforming, and then the type of transformed output elements. Okay. You can append a pipeline to a stream to transform the stream's output elements. You can pre-append a pipeline to a sink to transform the input type of the sink. You can also append two pipelines together and have a composition of transformations, so to speak. So here is your typical word count application, right? We are reading a file, and then we are decoding the bytes as UTF-8, splitting the decoded values on new lines, and then splitting again those values on spaces. We're then using runfold to count the number of words. Obviously, this is a very simple example here, but you can imagine implementing a complex business logic in such a manner where you define a series of pipelines that define specific aspects of your logic and then put them together to form one complete pipeline. Well, ZStreams are quite powerful, and they can help you streamline your business logic and create a code base that's easier to understand, and most importantly, in my opinion, maintain. ZStreams are surprisingly easy to use. Well, I guess due to the common sense approach adopted by its developers. I recommend you check out the Symposium series on ZStreams and the book Xenomicon for more in-depth views. That's all for now, and thank you for watching.